Hello and welcome to the Fun Kids Science Weekly, the show that takes you across the universe to learn some of the amazing secrets that are inside. And I think, to be honest, if we ever needed an excuse to escape across the galaxy, it's now, really, isn't it? If you're stuck at home, let your mind wander to some science with me. My name's Dan, thanks for listening. This week we'll talk about a deadly Bolivian jungle. We'll also hear about why slime could hold the secrets of the universe, and we'll chat about the energy of the future, imaginary energy, in just a sec. First, let's catch up with one of our favourite geniuses on the show. This is Professor Hallux.
Professor Hallux's Pathology Puzzles with the Royal College of Pathologists.
Time Stop Crime Cop again? I really don't get this new fascination with dead human beings. It's so, icky.
For the last time, nurse, it's Time Cop Crime Stop, not Time Stop Crime Cop. Or at least, I think it is. Anyway, it's not icky, it's pathology, medical puzzle solving, and it's not just to do with dead people.
Oh, I do remember that one episode with the curious case of the crinkly cop. That one got very fishy.
The type of pathology that's trying to work out why something or how something died is called forensic pathology. It's very important in case there's been a crime committed or a mistake made which caused death. If we know why things happen, we can try to stop them happening again. But anyway, forensic pathology is only one sort. There are loads of others.
So, can pathology be used to help people who are still alive?
Of course. Living people have just as many puzzling things happen to their bodies as dead people. Why do you think people go to the doctors? To try to work out why they're feeling crummy and to get the right treatment. Every patient is a puzzling case.
So what other types of pathology are there?
Well, there's anatomical pathology. That's about looking at tiny samples of human tissues under a microscope in a laboratory. Then there's genetic pathology. That's trying to figure out if the DNA in our cells is likely to make us poorly. And immunopathology, which is all about issues with the immune system. Then you've got your blood pathologists, also known as hematologists. If someone has a disease which affects their blood, these science puzzlers test and analyse their blood closely. If you have had a blood test, it's these guys who will have been on the case. And talking of being on the case, shush a bit, because Crime Cop is starting again.
I thought it was Time Cop.
Professor Hallux's Pathology Puzzles with the Royal College of Pathologists. Find out more at funkidslive.com/Hallux.
Right, it's time for one of my favourite parts of the show. It's where you send in your questions as a review to the Fun Kids Science Weekly over on the Apple Podcast Store, and then I do all the work trying to get the answer for you. This is from Amelie, who is 7. She's got another eyebrow-related question. This is inspired by last week's one, where we discovered just how important the eyebrow actually was for us, for keeping dirt and grit out of our eye, and also for displaying emotion to people around us. Amelie asks, how do eyebrows know when to stop growing? I think it makes sense, Amelie, to look at this in a wider context of the rest of the hairs on our body. You see, hair cells, they're all programmed, really, to grow for a certain amount of time. Now, through years of evolution, these cells have developed in a way to understand exactly what your body needs. So, hairs on your head, they'll grow for ages to keep your brain a really important source for you, to help keep that warm and safe. Hairs on your arms grow short, just to give a little bit of insulation, some air, trapping some air in there. And eyebrow hairs are told how long they need to be, when to stop growing, in order to keep grit and dirt from your eye. So it kind of works the same as it does for all the other hairs on your body, Amelie. Thanks for the question. This one is from Kitty. Kitty asks, why do mosquitoes bite someone many, many times before they finally fly away? Now, there's a lot of ideas about this, Kitty. We don't know. I don't think we can really investigate the brain of a mosquito to find out exactly why they're doing things. But one idea that the experts have got is very simple. When someone is bitten, usually they toss and they turn, don't they? If you were being bitten by a mosquito, you'd probably swat it a few times to try and get it off. So the mozzie has to keep coming back to try and get a full meal of blood. So that's one idea. Also, scientists think that maybe some people's blood type, you get A, you get O, you get B positive, or some people's blood type are not thinned enough by what's in the mosquito's saliva. Because that's what happens, you see. When a mosquito bites you, its saliva is filled with something called an anticoagulant, and it thins the blood, which makes you bleed more, and it helps you bleed through those tiny little holes that they make. So they get a bigger meal, a bigger lunch. Now, sometimes scientists think the saliva doesn't work effectively. The anticoagulant isn't that good at operating on some blood types, so the mosquito has to bite again and again for more food. And finally, this is from Audrey, who asks, why do we not bump our heads when we're in a lift? Nice and easy, Audrey. It's because the whole thing is moving with you. It's not just the floor. It's not just the floor squishing you into the ceiling. The ceiling is being pulled up as you are by whatever lifting mechanism is dragging you upwards. So there you go. Everything's moving together. Thank you so much for the question, Audrey. If you've got something sciencey that you want answered on this show, you need to leave it as a review for the Fun Kids Science Weekly over on the Apple Podcast Store. It's the Fun Kids Science Weekly. Now, we're hearing a lot about energy at the moment, with the current climate crisis making us think about what energy we've used and how we might need to change what energy we use in the future. So to help us understand this, we've got an expert on the show. Dr. Stephen Peake is a senior lecturer in environment, the Faculty of Science, Technology, Engineering and Mathematics at the Open University, and he's here to tell us more. Hey, Stephen.
Good morning. How are you?
Yes, I'm very well, thank you. And you've got all those words in your title, environment, Faculty of Science, Technology, Engineering, Mathematics. So you should be best placed, I think, to give us the wide spectrum of this. I don't know if it's too tough a question to start with. As scientists, how do you actually define energy? Because for us non-scientists, it's something that I think we take for granted, that we know about, but we don't actually know what it is. So as a scientist, how do you define energy?
Well, you're absolutely right. We have this word, which most of us will know, energy, and it can mean all kinds of things, like I'm running around in the playground, I've got lots of energy, or my batteries have run out of energy, or, I need some food, I need some energy. And so we use this kind of word, but scientifically, actually, it's a very tricky, slippery thing to define. It's not easy at all. And the way that scientists do it in its most advanced form is we get together a whole pile of mathematical equations, many of them, and we put them all in a blender, we turn it on, you get a vast, complicated sort of soup of equations, and we say, yeah, that's what we define the energy of a thing is. So it's really complicated.
When we're using the word energy in terms of powering us and powering our Earth, the energy given from electricity and from coal, and how much does that change what we think about energy and how we use it?
Well, that's yes, you're quite right. That our relationship with this thing, this mathematical thing that really is energy. It's maths really at its core. But our relationship with it isn't really like that. Our relationship with it is about the bag of coal that we might be carrying in, putting on the fire, the block of wood, the petrol that's going in the car, the chemical energy in the petrol, or the electrical energy that's coming out of a battery, or the gas energy that is coming out of the ground through the pipe into a house and being burnt in the boiler. All of these are different fuels. And so we're quite used to the idea that we need fuels and different energy sources, and they're all very different. And the food that we eat is another energy source. It's when we try to sort of be clever and more generic and put them all together that things get, they get quite interesting. And that's why my show is about re-engaging with the slipperiness of this concept of energy and the difficulty we've had in getting to the point we are now in science of explaining what it is, and what that might mean, interesting enough, for the future when we've got to do things a little bit differently. How does it, if we don't take this thing we call energy for granted anymore, and we really unpack it once again, a bit like we had to do 400 or 500 years ago when scientists were first trying to piece this jigsaw together, what the heck is going on? Actually, I think the key to the future lies more in the past than we think. And so it's time for us to stop taking it for granted, stop wasting energy, stop leaving the lights on, leaving the windows open, stop wasting this really precious fuel that we have, all the different kinds of fuel, start taking it more seriously. And within that, we'll discover how we have to be more careful and more imaginative, more creative in our relationship with it in the future.
Now, the show is on the 15th of April, and I'm just thinking, I can barely explain it myself. How do you get into it? You know, we had quite a trouble at the start of our chat trying to define what energy is. How do you possibly go about it? How do you get into talking about energy in a show with a few hundred people watching?
Well, imagine... what I try to do is get the audience to imagine what it might be like if they had been, I suppose, stranded, for example, on a desert island as a young person growing up without necessarily the access to all the books and all the science that we just get through our schooling. And if we were to sort of be on this island and we were to start sort of observing the world as it was, the waves, the wave energy, we hear that crashing sound, maybe we could start a fire. And maybe, so we noticed that some things burn and other things don't. And maybe we were getting clever, maybe some plastic washed up or something. Well, we shouldn't be washing up, but maybe it did. And we rubbed two bits of plastic together and we realized it was some sort of, made our hair stand on end. And we didn't have any real science, but what we had was our eyes and our ears and our senses, and we were beginning to say, well, gosh, this is really interesting. You know, some things have got this strange, mysterious thing, this heat in it. Some things haven't. Some things have got electricity in them. Maybe some things, some rocks stick together. There's something going on, and that would be what we now know as magnetism. And what I try to do is say, look, this is exactly how the world appeared to some of the great giants of science and that we rely on today, you know, Francis Bacon, Descartes, Leibniz, Isaac Newton, Bernoulli, Lavoisier. All these are famous names from the past who were chemists or physicists or mathematicians, and they were going around looking at the world with their eyes, just observing what they see without the benefit of all the science we have today, and they were putting these pieces together and thinking, gosh, isn't that interesting? And I wonder if there's this thing inside this material, and would that transmit into this other thing? And is magnetism the same as electricity? And is heat the same as gravity? And so on and so forth. So I try to remind an audience that actually it's not that long ago that we hadn't got a clue what energy was. And if we start there, then I can sort of gently bring them forward and get them to really appreciate and not take for granted what energy is today.
Without getting too mystical and new age on you, Stephen, it's always baffled me to think why it's taken us so long to be rekindled to the idea of renewable energy. I'd say before the Industrial Revolution and the advent of electricity, the world was pretty much powered by the sun. You know, the sun gives everything energy, and we're only really being awakened to that again now. Why do you think it's taken us so long to think about renewable energy and that the sources that we've been using recently aren't going to last forever?
Well, that's a really good point. You're absolutely right. For the vast majority of the history of the human species, 220-odd thousand years, Homo sapiens like us have been being clever and being creative. For the vast majority of that time, it's been using biomass, in fact. And then we got a bit clever and used wind, a little bit of early wind power, a little bit of water power, beginning to drive this sort of industrialization early on. All that's renewable, exactly as you say. It all comes from the sun. And then we discover fossil fuels. We discover coal and oil and gas, and we go on this enormous energy binge. What happened to us in the Industrial Revolution is that we said, wow, we can have concentrated ancient sunlight. We can dig it up from the ground in the form of a piece of coal, or get a barrel of it, some oil. This is concentrated ancient fossilized sunlight, and we can burn it all at once, and we can have a real party, and we can just burn it, and we can waste it, and it's just so cheap, and we just have this fantastic party, and that's what happened in the Industrial Revolution. Now, of course, what we're learning today is, well, there's lots of things. We're running out of some of this ancient fossilized sunlight. We haven't got inexhaustible supplies of oil, cheap oil left. We've certainly not got an awful lot of natural gas left, or cheap natural gas. So one thing is that it's a finite amount that we've got in the ground. But another thing is, we discovered in the last 30 years that when we burn fossil fuels and we pump that carbon dioxide into the atmosphere that's a result of burning fossil fuels, some of it stays there, and we're using the atmosphere as a dump. And as a result of that, of course, the greenhouse effect is happening, and that's increasing global temperatures for the atmosphere and the oceans, etc., and all the problems to do with climate change. And so the reason we're going back to renewable energy is because, A, we're running out of that fossil fuel that we have just been having a great party on, but B, we realise that burning it isn't good for our future because it's warming the planet, and there are all kinds of problems that we face if we burn all the fossil fuels that we've got left. But we're not going back to ancient old windmills. We're not going back to old water mills. We're going forwards to really advanced photovoltaic solar power, concentrated solar power farms, amazing, huge wind turbines the size of a giant aircraft wingspan. I mean, we can produce renewable energy in a modern way, which is just so fabulously fantastic and very cheap, relatively cheap, actually, as cheap as fossil fuels are in many cases now. So the future is just amazing, and it's renewable.
Well, let's talk more about the future. What you were just speaking about seems to me to be able to help us out perhaps in the next century. But what we should learn from the past 200 years of willy-nilly burning fossil fuels without really much thought is maybe we don't need to think about just the next century, but the next 3 centuries. We need to think that far ahead. Stephen, as someone that knows a little bit about the future of energy, your show is called Imaginary Energy. I mean, how are we thinking of dealing with this way in the future?
Well, way in the future. Well, I think we're going to be drawing energy from sunlight directly every day for the rest of our existence. So we're just going to get cleverer and cleverer at doing that. One of the problems is that we still have a problem of storing energy. Now, fossil fuels are a very good store of energy, and that's done naturally over millions of years. And we still really, to have a modern economy functioning, we still need to have little spurts, little concentrated boosts of energy. And so we still have to store this renewable electricity that we generate. So in the future, we're going to get really clever about the relationship between, for example, the electricity that we generate during the day through sunlight or when it's windy, and how we transform that, for example, into hydrogen, which we can then store safely, which then can be drawn on when we need sudden boosts of energy. And I think the future is a combination of advanced solar power with hydrogen power. And I think that's really, unless of course you want to get sort of all sci-fi and we have there's a bit of physics that we haven't worked out, and that there's some hidden equations in matter which still haven't revealed themselves, and we can somehow get some new kind of nuclear or fusion energy that no one's kind of figured out yet. I mean, that's still potentially a possibility that some sort of advance in physics that hasn't happened yet could happen. But I think barring that, the future is clear for the next 2, 3, 4, 500 years is going to be renewable energy and hydrogen. But more than anything, the one energy source that everybody forgets about as they get carried away thinking about science fiction the one energy source we've got is to stop wasting energy, because energy efficiency or energy conservation is the biggest kind of source of energy. Because if you don't waste energy, you don't need to run around trying to find and scratch around trying to build energy systems everywhere, because you're not wasting it. You don't have to use as much. So I think the future will be using very cleverly small amounts of energy to do just precisely the amount of work that is needed. So we'll use, the internet, the Internet of Things, the smartness of devices, the smartness of cities, the smartness of transportation systems. It'll be an incredibly smart future where we don't waste, and what we do produce is produced by sipping the daily sunlight and perhaps storing it with hydrogen.
Well, there's a lot to look forward to, especially a physics equation that we've not quite worked out yet. Dr. Stephen Peake, thank you so much for joining us.
Thank you very much. It was a pleasure.
Now, for this week's Dangerous Dan, we're headed into the jungles of Bolivia, South America, to take a closer look at the Madidi National Park. It covers almost 19,000 square kilometres right in the heart of the Amazon. It's a spectacular place with wildflowers and trees and rivers and bright colours all around. Also, it's one of the most diverse places on Earth. And because of that, it's home to its fair share of deadly beasts. Over 120,000 different insect species call it home. It's also got snakes and bears, but caimans. You might even spot an elusive jaguar in the shadows ready to pounce. Also, it's home to wild pigs. Wild pigs don't sound too deadly, but they are ferociously dangerous, known to tear humans apart and leave them scattered around the forest floor. Also, to get there, you probably need to take what's known as the Bolivia Death Road. You might have seen this online or on the telly. It's like a thin road. It hugs a cliff, but hangs over into an abyss, into nothingness. Nothing is on the edge as well to stop you from tipping over. Now, there's a lot to admire at the Madidi National Park. Problem is, you need to climb over the man-eating bears and cats and birds and spiders and snakes and pigs to find it. Right, let's get some of your gadget questions answered. How technology is helping us and the world around us with Technomum.
Technomum, Engineering Explorers.
Typical. Trying out my new electric scooter and I've come off and grazed my knee. Looks like my trousers are ruined too. Why can't someone invent super strong skin? That way we wouldn't get painful grazes like this one.
Hold still. I can't get the plaster on if you keep flinching.
Ouch! Skin is rubbish. I wasn't even going that fast and I've got a massive cut and a bruise now.
Hush. Skin's really amazing stuff. It does a great job at keeping the bits inside our bodies, well, inside. It also helps keep them at the right temperature.
Come on, Mum. Even you know there's always room for improvement. Ouch! This knee would definitely be improved by being healed up instantly with, say, a special instant skin replacement cream.
I don't think instant skin replacement cream has been invented yet, but there are people who use engineering to help us stay in good health. They're called biomedical engineers.
Biomedical engineers? What's that all about?
Well, biomedical engineers might be inventing new products such as replacement joints or surgical instruments. Or they might be trialling super tough metals or mega flexible polymers to help keep joints moving for longer.
Hey, that'd be cool. You could have Gran doing the high jump at Gran Olympics.
I'm not sure she'd like that. Other biomedical engineers might be adapting equipment that's already in use to help people who can't easily move their bodies to communicate, or even write and paint, by using sensors and computers which translate the movement of their eyes.
That's pretty cool.
It's not just cool, it can be life-changing stuff. Now let's not forget the really futuristic stuff. You've heard of nanotechnology, right?
That's like the science done on a really tiny scale, building things at the molecular level.
Yep. Well, there's plenty of biomedical engineering which gets down to the cellular level, creating treatments and medicines which work within the cells of our body, say to deliver drugs to the exact place where they're needed. Biomedical engineers might be working with materials like metals and plastics in a workshop, or using IT and computers in an office and coming up with a brand new creation in a laboratory. Check out this video. It shows some really exciting stuff that's being done with skin.
Magic skin replacement spray? Ew, no. Looks like a test tube. Where's the human body?
There's no body. The engineer is working on a sample of human skin. It's that white substance in the dish.
Whose is it? She should give it back.
This skin wasn't taken off anyone's body, but it did come from some human cells. Stem cells. Some biomedical engineers are working to create pieces of skin in the laboratory which can be used to help people with injuries such as burns.
I could use a bit of that. Help my graze to heal up.
I think you'll survive with a plaster.
Cool job, though.
There are loads of cool jobs for engineers. Almost as many jobs as there are inventions.
That's great. Hey, maybe someone can invent trousers that never split.
Engineering Explorers, created with support from the Institution of Engineering and Technology to celebrate the Year of Engineering. Find out more at funkidslive.com/technomum.
Now it's time for this week's Science in the News. Evidence has emerged that at one point in history, the Falkland Islands off the coast of Argentina may have been hit by a tsunami, and it may be hit again. Scientists have used computer models to see how much damage underwater landslides would have done, and predicted that it might happen again in the next 1 million years, so nothing to worry about too soon. Also, one of the UK's most popular wildlife tourism destinations is getting a makeover. Purbeck Heath in Dorset will be expanded and revitalised to attract a wilder array of wildlife. And finally, this is a big one as well, listen to this. Scientists think slime tends to mirror the structure of the universe. Slime mould looks like it takes the shape of how the universe spreads out, how it spreads its tendrils, really, and how it connects the galaxies. And scientists, having discovered this, are studying slime mould to see how it can help us understand dark matter. And that is it for this week's Fun Kids Science Weekly. Thank you so much for giving us a listen. As always, if you've got a science question, fire it over to the podcast page. Leave us a review over on the Apple Podcast Store. Find the Fun Kids Science Weekly. Leave us 5 stars as well, and drop your name. It gives me a much better chance of seeing it. Remember, I'm after your train questions as well. Got a few on there. I'd love some more as a review over on the Apple Podcast Store. It's filled there as well with so many amazing science series that we do at Fun Kids, which might come in really handy right now if you're stuck at home, give you something to keep busy and listen to. You can find them on the Apple Podcast Store, on the free Fun Kids app, and at funkidslive.com. And Fun Kids, we're a children's radio station from the UK. You can hear us all around the country on your DAB digital radio, on that Fun Kids app, and as always at funkidslive.com.